On Monday, we were reviewing certain variables associated with the analysis of deformable bodies. And the first of these variables is stress. We have shown that 6 independent components of stress are needed to define stress states at a point. In a general three-dimensional problem, a total of 6 different stress components are needed. And the second variable we will be defining here is strain. And we will consider the definition of strain today. The next title is therefore strain. The change in the shape of the body is defined in terms of strain. This could be a change in the size of an infinitesimal vector and that is the rotation corresponding to the deformations. There is a size change as well as orientation change. And the orientation change in the body is quantified by considering such infinitesimal vectors, 2 vectors that are perpendicular to each other can be considered, and the change in the angle between those 2 vectors gives shear strain. And stretching of an infinitesimal vector, as shown here, gives normal strain in the direction of this infinitesimal vector. And we can simplify these for small deformations. First, we can define a deformation vector. Suppose that this is the undeformed configuration for a general deformable body, general undeformed shape. And under the effects of forces, you will observe a shape change, and the dashed line stands for the border of the deformed body. This is deformed. And you can define a displacement vector for each of the points on this body. Suppose that a generic point is represented as P. And under the effects of forces, this P will displace to another point, P prime. And the vector connecting these 2 points is the displacement vector for P. It's shown as delta here. In our representation, we will write delta as a function of the coordinates of point P, which are x, y, z. Delta of x, y, z is written here. It has 3 components, as you see, u, v, and w. These are the scalar components of the displacement vector. And each depends on the coordinates of point P, x, y, z. We have a coordinate system. We are defining the displacement vector in this coordinate system. Thus, in this representation, we need the corresponding unit vectors, I hat, j hat, and k hat. These are the unit vectors. That's the definition of deformation or general displacement, but this is not strain. Strain is a dimensionless quantity. And how can we define strain? To be able to simplify this derivation, we will start with a special case. We will not consider a fully three-dimensional case here. It's a special case plane strain, and later we will talk about fully three-dimensional results. They are exactly the same as those found for plane strain. And what are the assumptions or what are the conditions related to plane strain? This x component of displacement is a function of xy. My component of displacement is a function of xy, that's b. The z component of displacement is 0 in plane strain. That is therefore planar deformation, and all deformations take place in xy plane. A point in xy plane remains in xy plane. However, in z direction, the displacement is 0. This is achievable for an infinitely long cylindrical body, but it is a good approximation for other types of cylindrical structures, for which the length is much larger than the in-plane dimensions. But our here objective is to find components of strain. And how can we find this? This is an elastic body, general elastic body on the plane strain. It's loaded on the boundary by surface forces. We consider the specific coordinate system xy, and these are infinitesimal lines dx dy located at a particular point. This body is supported around the periphery. And how can I present strain mathematically? We start with two infinitesimal lines in y and x directions as shown here. And these lines are bordered by the points A, B, C as shown. Dx and dy are lengths of the infinitesimal lines. And consider displacements of point A. This is point A. Consider its displacement in x direction as u, xy. This will move to point A prime, and B will move to B prime, C will move to C prime. This is the x component of displacement. This is the y component of displacement for A. Now we have a new triangle, A prime, B prime, C prime. The vectors are, the lines are stretched. It's A prime, B prime is the new length. And they are also rotated through angles θ1 and θ2. The x and dy are original lengths. And we can examine this figure, apply Taylor series representation to find definitions or expressions of strain for this point. We are looking into expressions of strain for point A. And how do we do this? This is x displacement of point A. And it goes to A prime. What about point B? How can I find x displacement of point B? This is found by applying Taylor series representation Now, expand U into a Taylor series around A. The next point is V. And Y is constant here. Now, first order Taylor series is U plus du dx at A times dx. And we neglect the higher order terms because the points are close to each other. We are looking into behavior of an infinitesimal vector to define strain. And now this is written as a Taylor truncated Taylor series. And now in this second diagram, I can find this length x component of this deformation vector. This length can easily be found actually. And how can we find this? I'm talking about this component of the deformation vector, this component. It's the whole length covering the whole distance is the x plus u plus du dx dx. Subtract ux plus dx, and you will end up with du dx dx. It's not so difficult. Along the other direction, A in y direction goes to A prime. The deflection is V now at point A. And the other point B will undergo a vertical deflection given by V plus dV dx dx, because the variation is in x direction here, and dV dx is computed again at A as Taylor series presentation. The difference gives this amount of deflection here, which is dV dx dx. Now, you can apply the same procedure to find this length, which will be expressed as dV dy dy, and this length can also be found. So this diagram for infinitesimal vectors allows us to define strain components. We can define different strain components. Normal strains and shear strains can be defined. First, define shear strain in x direction. Shear strain in x direction, normal strain in x direction is defined by considering an infinitesimal vector in x direction. And change in length of this vector divided by the original length is normal strain in x direction. That is at point A. Epsilon x is therefore A prime B prime minus AB over AB. This is epsilon x. AB is dx. Replace AB by dx. Then I can write A prime B prime as epsilon x plus 1 dx. This is by definition. Another way of finding A prime B prime is to use this diagram, deformation diagram. A prime B prime can be written by using the triangle. It's this side square of A prime B prime is this side squared plus this side squared. Or A prime B prime squared is dx plus du dx dx squared, here on this side, plus dv dx dx squared, that's the vertical side. And expand this, expand this. And you can factor out the x squared. It's going to be written in this form from the displacement diagram. This by definition, if you take the square of the definition, you will get epsilon x squared plus 2 epsilon x plus 1 dx squared. And I can equate these two to find epsilon x. Equate these two. Equate the expression obtained from the triangle to that found by applying the definition. So I have such an equality. And how can I simplify this equality shown here? Any suggestions on this? How can we simplify this result? Now, we have to know something related to small deformation theory. We will be using small deformation theory for composite bodies, linear elastic composite bodies. It states that strains are infinitesimal components, infinitesimal quantities. They are small, and which implies that epsilon x squared is negligible compared to epsilon x. Ones are canceled out on the left and on the right. And furthermore, slopes are infinitesimal quantities in small deformation theory. Is the udx, the vdx, these are slopes. They have to be small, and their squares are negligible compared to the slope itself, shown here. Which means that in small deformation theory, the udx is epsilon x, or epsilon x is found. Strain at point A is this derivative du dx computed at point A. Any questions or comments related to such definitions? Now, you can define, or you can compute epsilon y following a similar procedure, and which vector is the starting point here to define epsilon y? Which vector can you use? Any answers here? We have used AB, vector AB, to define epsilon x. And of course, you have to consider length change for vector AC to define epsilon y. This could be asked in the quiz or the homework, which means that if you follow a similar procedure, you will end up with such an expression. Epsilon y is dv dy. Second normal strain. And the third strain we will define is named engineering shear strain at point A. And it's changed in the 90-degree angle shown here. The angle between AB and AC is 90 degrees. And the change in the angle, this angle, minus this angle, is engineering shear strain. Thus, engineering shear strain has to be equivalent to θ1 plus θ2. Sum of these angles gives engineering shear strain. It's defined by gamma xy, and it's equal to θ1 plus θ2. What are θ1 and θ2? Again, you can find them using this diagram or the triangle. Tangent θ1 equals dv dx 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 plus over dx plus dx dx. This is tangent theta 1. It's written here. Tangent theta 1 is dv dx dx over dx plus dv dx dx. Again, consider small deformation theory. Slope du dx is an infinitesimal quantity. It can be neglected in the denominator here, and you end up with dv dx for tangent theta 1. However, these angles should be small because you see that slope of this line is now dv dx in small deformation theory. And this angle, therefore, has to be small. It's consistent with our assumptions. Tangent theta can be replaced by what for a small angle? How can you replace tangent theta if the angle is small? Any answer? There are some answers, I think. Yes, Hussein gave the correct answers. It's theta. It's replaced by theta 1. Tangent theta 1 is equal to theta 1. It is dv dx is the slope of this line. And tangent theta 1 is therefore theta 1, and theta 1 is dv dx. You can show that theta 2 is du dy here. It's theta 2. It's the other slope. Slope is the angle. And from small deformation theory, theta 2 is du dy. And thus, we have an important relation for engineering shear strain, again, based on rigid body rotations of vectors. Gamma xy is du dy plus dv dx. You can measure this. Actually, such measurements are made in certain applications. You can mark small lines on a deformable object, and you can keep track of their deformations. And that's going to give you the strain at that point experimentally. And there are certain ways of keeping track of deformations, optical methods, and other types of methods. Or strain gauges are used directly to find normal strain, principal strains on the surface of a deformable body. But these results, epsilon x, epsilon y, and gamma xy, they are found by considering a state of plane strain, a two-dimensional state of deformation. But it's possible to do three-dimensional analysis, fully three-dimensional analysis by considering infinitesimal vectors in 3D space. It's a tedious procedure, but you will see that you will end up with exactly the same representations for strains, but that's going to cover whole strain components. Under a general three-dimensional state of deformation, we can define epsilon x, y, z. And epsilon z is the w dz, as well as gamma xy, gamma xc, gamma yz. These can all be defined. These are engineering shear strains. There is a second strain definition, important strain definition. It's called tensorial shear strain. It's given by this formula, tensorial shear strain epsilon ij, where I is not equal to j, is 1/2 gamma ij. It's half of the engineering shear strain. That is epsilon xy is 1/2 gamma xy. When you place the tensorial shear strains in a matrix along with normal strains, that matrix will obey certain transformation formula, tensorial transformation formula. For this reason, these are named as tensorial shear strain, but you should know both definitions depending on the given data. You might need to use either engineering shear strain or tensorial shear strain. Any questions or comments on this? Do you have any questions? There's an example here. A displacement field in a body is given by these expressions. U, for example, is given as a function of x, y, z coordinates 10 to minus 5 times x squared plus 6y plus 7xz. V is 10 to minus 5 yz. W is 10 to minus 5 xy plus yz squared. xyz and u, v, w are all in millimeters here. Find the state of strain at this point. What is the state of strain at this point? That's the question. What are the strain components? Normal strains and shear strains. You can find yourself, find epsilon x, for example. Calculate epsilon x and tell me the result. What is epsilon x for this problem? You can try to find epsilon x first. Let's see if there are any answers. What's epsilon x here? Any answers on this? Can anybody find epsilon x? It's V. This is W. Epsilon x. You need to use the definitions to find strains. Epsilon x is du dx. So these types of problems will be asked in the quiz. Epsilon x is du dx. You need to differentiate it with respect to x. Derivative is 2x plus 7z. Substitute values of x and z. And at this point, so we had to keep the coordinates as well, right? You could find epsilon x. You could have found this 10 to minus 5 times 2x plus 7z. That's epsilon x. If you want to find a numerical value, we need to provide the coordinates at this point 1, 2, 3 millimeters. That's 2.3 times 10 to minus 4. This is epsilon x. What's epsilon y? Is dv dy. And what's dv dy? Is 10 to minus 5z. Substitution leads to 0.3 10 to minus 4. gamma xy engineering shear strain is du dy plus dv dx. Du dy is 6 times 10 to minus 5. What is dv dx here? Is anyone following this? What is dv dx? Yes, Hussein, Amar, Ali, and Khalil, they are following. And dv dx is 0, that's right. Which means that gamma xy is 10 to minus 5. So you can easily find all strain components, remaining components out of plane components are epsilon z, gamma xc, and gamma yz. They can all be found symbolically or numerically. As the strain, these are the strain and displacement fields. They are representative of deformations of infinitesimal lines. It could be stretching for positive strain, contraction or negative normal strain, and you can find distortion by computing the slopes or the rigid body rotations. Sum of the rigid body rotations gives the strain in a given coordinate system. But these are known definitions, and you'll be able to compute strains. And these relations are also named as kinematic relations for small deformation theory, except a set of differential equations, actually, or simply strain displacement relations. And we will later make use of this, especially when we develop a plate theory to examine behavior of composite laminates. We have considered definition of stress and representations of strain components. And a third factor in formulation of solid mechanics problems is the constitutive relation. That is material behavior, and it's identified in terms of elastic constants for linear elastic materials. We will actually deal with relationships involving stresses and strains, not forces and displacements, but stresses and strains. This is known as Hooke's law in study of isotropic linear elastic solids, but it's still Hooke's law, but generalized Hooke's law when we consider behavior of composite materials or anisotropic materials. And it's written in terms of elastic moduli. These are material properties for isotropic materials. A composite body is not isotropic, but you can start with this main case. What's the constitutive relation for a linear elastic isotropic body? That's the constitutive relation. And it involves strain vector consisting of epsilon x, y, z, gamma y, z, gamma x, z, gamma x, y. We always use this order or this representation. And it's compliance matrix times stress vector. And if you are familiar with such relations, you have already used this in different types of analysis in strength of materials or machine elements. such representations are always needed. And for an isotropic material, what is the relation? Epsilon x is, for example, equal to 1 over E sigma x minus nu times sigma y plus sigma z. Epsilon x depends only on normal stress components. And there are zeros here, which means that this epsilon x does not depend on shear stresses. What is E called? What is E? I'm sure you know what E is. Yes, Hussein gave the correct answer. E is modulus of elasticity. What's nu here for this isotropic material? What's nu in this formula? Yes, Hussein, Ahmed, Arif, Murtaza, they gave the correct answers, and they said, yes, that's Poisson's ratio, an important material property in analysis of materials. And all normal strains have the same structure. They don't depend on shear stresses if the body is isotropic. And generic shear strain can be written in a simple way. Gamma is tau over G for all cases. And G is shear modulus. That's another elastic property. But all three of these material properties are not independent. Two of them can be independently defined. G depends on E and nu. You can find G in terms of E and nu. Therefore, linear elastic isotropic body is identified by only two elastic constants. Two elastic constants are sufficient to define behavior of an isotropic body. And G is written in terms of E and nu. G is equal to E over 2 times 1 plus nu. You can refer to your strength book for derivation of this. And we will keep these equations in matrix form. Epsilon is now S times sigma. This matrix is called compliance matrix for an isotropic material. Compliance matrix is unfortunately denoted by S. And epsilon is S times sigma. I can invert this to write stresses in terms of strains. Find the inverse matrix here. Find the inverse of this matrix, S. Inverse will be shown as C. And then the relationship becomes sigma equals C times epsilon. C is stiffness matrix. When you write stress, then the matrix is named as stiffness matrix. And stiffness matrix is inverse of compliance matrix or vice versa. How can we invert this? You can use one of the procedures of linear algebra to invert this symbolically, but we don't do that. We'll be using math packages to directly find inverses of such matrices. I will talk about this inversion in the next hour, in the second hour. So now we can have a break and we will carry on after that.